a polygon is any figure that has the following characteristics or properties. First, the first thing the polygon must do is it must be made of line segments. Its sides must be line segments. Its second property is that it must be what's called closed. The sides must all be connected. You can't have just openings laying around. It can't be an open polygon. It's got to be closed. All the segments have to be connected all the way around. And thirdly, and lastly, the sides are connected only at their endpoints. The last one will prevent us from having like figures that are like twisted on each other or kind of double back on each other that overlap. We can't have any of those. There are two very general types of polygons. There are convex polygons and concave polygons. Okay? A convex polygon is a polygon that in kind of non-mathematical terms would be a polygon that's always kind of going out, bulging out. Versus concave caved in on itself or like dented, something going on along those lines. You may have heard these words before in like science with like concave, like lenses, concave things. Never heard these words before? Yeah. In particular, a convex polygon is defined to be the following. Is that any polygon that if you extend any side the line extended never enters the interior of the polygon. The definition of concave is pretty simple. Concave is any polygon that is not convex. An example of a convex polygon might be the following. How about sure. We'll just make a four-sided figure here. This has got to be convex because if I extend any side, if you extend any side, those sides that we extend are always on the exterior or just on the side of the polygon. It's never on the interior. Versus a concave polygon might look something like this. Here's a really easy example. If you drew this simple shape, it's possible to draw a line through one of the sides so that it goes in the interior. Namely, here's an easy one. Namely, if you extend this side, this piece is on the interior. So this means if it's on the inside, it's got to be concave. So very quickly, is the first example here convex or concave? This is a convex polygon. Is the second one concave or convex? Okay, and prove to me why. Draw me one of the segments so that it's got to be to show me that it's concave. How would you prove to me why? Yeah.
That any line extends inside of it.
Any line, so if we extend like this one, then you got that piece right there. So it's got to be. It's got to be concave. We can name polygons by their sides. This table appears in your book. I forgot what page. It's like page. This table is on page 43 in your book. I'm not going to go through the common ones that you should already know, like 3 is triangle, quadrilateral is 4, pentagon is 5, hexagon is 6. You can go with either septagon or heptagon for a 7-sided figure. Either the Greek or the Latin version of the prefix for 7, septagon or heptagon, I don't care.
Why is September?
What?
Because they started.
8 is octagon. 9 is a nonagon. You can copy this down your own. If you already have it memorized, don't jot them down a second time. 10 is a decagon. 12 is a dodecagon. Anything that's not one of these very common ones, the ones I just named, we can call by the number of sides gon. So like 11 gon, if it's 11-sided figure, we'll call it a 11 gon. It sounds pretty dumb, but it's not very hard. 15 gon. If it has n sides, we'll call it an n gon. Okay? Those things you should know on your own. What's a 4-sided figure? Quadrilateral. Pentagon, hexagon. Those are like things you gotta know. You should already know. An equilateral polygon, what do you think is going to be true? All sides equal in length.
Where?
I know. If it's an equilateral polygon, all sides the same length. Equiangular, all interior angles. Are the same measure. And if it's regular, it's both of the first two. We'll call a polygon regular if it's both equilateral and equiangular.